I've chosen to make this program about induction motors because they make use of the three electromagnetic principles that we've dealt with in this course in a most ingenious manner. Briefly, what happens in an induction motor is this. A varying current is applied to some coils so that they generate a varying magnetic field. Then a loop of wire, which is freely suspended so that it can rotate, is placed in this varying field, and because a changing field produces a current in a conductor, a current is induced in the coil. But this current then interacts with the field which generated it and produces a force. And it's that force which causes the coil to rotate. And as you can see in this arrangement, the coil is rotating quite freely, being driven by the changing magnetic field generated by these coils. So that's, in very simple terms, what an induction motor is like. In a moment, Professor Eric Laithwaite from Imperial College, who pioneered much of the development of linear induction motors, is going to explain in more detail how the induction motor works. But first I want to revise some of the electromagnetic principles on which the motor depends. Now, the first principle is that an electric current generates a magnetic field. Here I've got an electric conductor mounted vertically through which I can pass a current. And next to it there's a little magnetic compass to show the direction of the magnetic field generated by the current. At the moment, the compass is pointing north-south due to the Earth's magnetic field. But when I pass a current through this conductor, by switching the current on, you'll see the compass pointer turns round to point in the direction of the new magnetic field, and as you can see, it's pointing along the circumference of a circle with the conductor as the center of the circle. This is because an electric current produces a magnetic field which forms circles round the current. If I reverse the current, you'll see the pointer points in the opposite direction, again along the circumference of a circle. Reverse it again, and it goes back to where it was before. So that the current produces a magnetic field, and the direction of the current determines the direction of the magnetic field. So that's the first principle, that an electric current generates a magnetic field. The second principle is that a conductor carrying a current in the presence of a magnetic field experiences a force. And I can show you that in another demonstration. Now here I've again got a vertically mounted conductor, but this time the conductor is free to move, so it can respond to a force which acts on it. If I pass a current through the conductor, the light comes on, but as you can see at the moment, apparently there's no force acting on the conductor and it doesn't move. But if I put a magnetic field around the conductor, so that now the magnetic field is from north to south pole of the magnet, the current is going to move either vertically, either up or down. Let's see what happens to the conductor. I switch the current on, and the conductor is moved away from the magnet. If I reverse the current, the force on the conductor is in the opposite direction. I can move it backwards and forwards by just reversing the current. So, the force is certainly dependent on the current flowing and is reversed if the current is reversed. What happens if we reverse the magnetic field? I take the magnet away, turn it over, and you can immediately see that the force is reversed in direction. So the direction of the force is reversed whether I reverse the current or whether I reverse the magnetic field. Now at the moment, the force and the magnetic field and the current are all mutually perpendicular. Remember the left-hand motor rule. Let's see if we can adjust the magnetic field so that it's in a direction which is in the same direction as the conductor is free to move. And if I've got it placed in exactly the right position, not bad. When I put the current on, no movement occurs, so there is no force to speak of in the direction of the magnetic field. It's always at right angles to the direction of the magnetic field. It's also at right angles to the direction of the current. So that's the second principle, that a current in the presence of a magnetic field experiences a force. The third principle is that a voltage is generated in a conductor when it is in the presence of a changing magnetic field. And I can easily demonstrate this with a coil and a magnet. First, I'll get these out of the way. Here's a coil, and here's a magnet, and here's a meter ready to record any current or voltage that is induced in this coil. If I move this magnet into the coil, I hope you can see that a current is indeed generated in the coil and is recorded in the meter. If the magnet stays still, there's no current generated. Only if the magnet is moved is the current generated. In fact, the faster I move it, the bigger the induced current, because the voltage is proportional to the rate of change of flux. So moving the magnet in and out of the coil, you can see I can generate an alternating current. It responds to movement, not to a stationary magnetic field. So these then are the three principles on which the induction motor depends. Now here's Professor Laithwaite to explain more about the induction motor.
I'm going to explain to you how an induction motor works. Here are two magnets on a rotatable arm, and as you know, magnets will attract pieces of steel, but not a piece of copper. And this disc is made of copper and is also free to rotate. There's about a 1/4 of an inch gap between the magnets and the disc, yet when I rotate the magnets, I also rotate the disc. Now at the moment, this is not a motor, it's a clutch, because you have to supply mechanical power in order to get mechanical power. What we'd really like to do to make a motor is to replace this rotating magnet system by something stationary fed with electric current that does the same job. What we use is a ring of coils like this. If we offer this ring of coils to the other side of the disc and feed them with the right kind of electric current, they will produce the same rotating effect and succeed in rotating the disc, and then we have a motor. But to explain how these coils do that, it's often easier to mount the coils in a straight line to begin with, like this. The current in each coil rises and falls, like that, so the magnetic field it produces also rises and falls, but not in the same time sequence as its neighbour. The two work together rather like that. And I can explain this better by means of a mechanical model. Instead of a row of coils, we have a row of rods, and each of these rods is free to move up and down in a slot. So the rod is moving up and down like the magnetic field was moving up and down. If you look at this end rod, that is all it can do. And yet, when you turn the handle, driving all these cams, you appear to have made a travelling wave, which can be reversed. It's rather like a wave in the sea. If you've seen a bottle cork on the wave in the sea, you know that the bottle cork only goes up and down as the wave passes. But when you put an object into the travelling wave, it will actually be moved along. In this case, the ball is moved along by the rods. In the case of the magnetic field, a piece of conductor will be moved along by the travelling magnetic field. Now I'm going to make the travelling wave using this row of coils. To do this, I've got a set of steel strips I'm going to bring these alongside so that the strips fit over the row of magnets. Now, when I switch on the current, you can see the familiar travelling wave pattern, this time produced by the actual magnetic field rising and falling in sequence. Now it's only necessary to complete the induction motor to take that away again, put a strip of steel on a track over the top of the magnets to make the field stronger, and get a piece of copper. When I put this into the travelling field, it's the equivalent of putting the ball in the mechanical travelling wave. And there is your induction motor. We'll do that once more. Now, on our original mechanical model, we had 12 phases. And you see what a nice, smooth wave that makes. When we come to make commercial machines, we want all those 12 phases in to make an efficient motor. And we do this by winding the coils around several magnets at a time. Now, this commercial motor is a very good propeller of pieces of aluminium and copper. Now, this straight line motor, of course, has practical applications. Now, by arrangement of the phases of the coils, it's possible to send a sheet of aluminium along a track in a very controlled manner, like this.
To achieve this motion, the horizontal travelling wave is directed towards the centre from both ends. There is also a vertical travelling wave which balances the force of gravity to keep the plate suspended in mid-air. One barrier to the successful application of this system is the sheer cost of energising a length of track. So the logical solution is to energise the vehicle and make the reaction sheet the track. This is the track of the first magnetic levitation train opened at Birmingham Airport in 1984. A 600-volt supply provides the power for the system. Passengers travel between the mainline British Rail station and the airport in a driverless system which brings together the basic principles of electromagnetism that we've looked at so far. The vehicle carries the sets of coils that generate the travelling wave, and the reaction rail is the central metal strip stretching the full length of the 600-metre track. So how exactly do the components which levitate and propel the vehicle work? One of the people responsible for bringing the system into operation is Eric Dalgleish of the People Mover Group.
There are two prime components, the magnets which provide the suspension and the linear motor which provides the propulsion. The magnets are energized by direct current and they lift the vehicle to the flying height of 15 millimeters above the track. The linear motor propels the vehicle by providing thrust due to reaction with an aluminium and steel plate along the center of the track. The whole secret of the maglev is the control of the electromagnets so that the vehicle is suspended just at the correct height of 15 millimeters above the track.
One question you may be asking is, why doesn't the magnet lift the train up until it hits the rail? After all, a constant magnetic force would surely do that.
Well, if it were just a plain standard flow of current through the magnet, that is exactly what would happen. But this is the secret of the control system, that as the magnet rises, the current is reduced so that once it gets to its correct floating height, it is just the correct current to maintain it at that height, and it is kept like that whilst the vehicle is flying. The power for the vehicle in toto is drawn from two conductor rails underneath the track at 600 volts DC and is converted on the vehicle into three-phase AC, variable frequency, variable voltage, to provide the necessary power to drive the linear motor.
Now, up to now, we've only been talking about flat motors that produce motion in a straight line. And most electric motors, as you know, produce round and round motion. With this rubber model, I'm able to show you all you have to do, which is to bend it round into a cylinder and join it. Now, when that's been engineered, it looks like this. Now, any loop of wire which can rotate, put inside such a cylinder, will spin once the field has been switched on. Now, it may occur to you that that's rather wasteful, just to have one loop inside all that space. So what we do in a conventional motor is to have lots and lots of conducting loops to fill the middle with iron to make the magnetic circuit more efficient. And if I bring back my rubber stator, put the rotor inside, roll it up and seal it, and there is a model of a conventional induction motor.
Finally, I'd like to enlarge a little on the explanation given by Professor Laithwaite of how rotating magnetic fields are created and how they interact with the rotating coil in an induction motor. Professor Laithwaite showed that if you take lots of coils and lay them out in a line and excite them in sequence, they produce something very close to a traveling magnetic field. What I want to show here, the first point I want to make, is that if you take these coils and wrap them round in a circle, as in a rotating induction motor, they all act on the same volume of space where the rotor is between the coils, and so it's very much easier to produce a rotating magnetic field. The net field in this space is the vector addition of the fields produced by these various coils. Now, most induction motors contain three pairs of coils, or three fields, at 120 degrees to each other. And this is because the mains field, the mains current, is generated in three phases, which is just what's needed for a three-phase motor. But you don't need three phases. You can make an induction motor with only two phases and two fields at right angles. So what I want to do first of all is to show how such an arrangement of fields, excited by sinusoidal currents, can generate a rotating magnetic field. Here is the demonstration that I showed you at the beginning of the program. Here we've got two coils at right angles to each other. They're both being driven by sinusoidal currents, and the result is that this little coil of copper wire, there's no connections to it, placed in that field, is caused to rotate by these fields. Now, the question is, how does this come about? And I want to explain this by an analogy with electric voltages applied to the plates of an oscilloscope. So let's have a look at this oscilloscope. Here we've got two sinusoidal waveforms. They're the same frequency, but they differ in phase by 90 degrees. Now, to simulate the behavior of the induction motor, I've got to take these two waveforms and apply them, one to the X plates and one to the Y plates. At the moment, they're both applied to the Y plates with a time base so that you can see that they have a phase relationship with each other. But now if I put them on the two pairs of plates separately, the result is a circle is being generated. But you can't see at the moment that this is a circular field, a rotating field. So if I reduce the frequency to a much lower frequency, about 1 cycle per second, you can now see that the spot on the oscilloscope screen is rotating. And what's happening is that One voltage is being applied to the X plates, and so moving the spot from side to side, as you can see at the moment. The other voltage is being applied to the Y plates, and it's moving it up and down. If I apply the voltage to both plates, and if they are out of phase, the result is that the spot rotates. Now let's think for a moment what this spot represents. The position of the spot relative to the 0 point is the voltage that's being applied to it. So it's being moved up and down and from side to side. But since it's moving in a circle, this means that the strength of the field is remaining the same. But the direction of the field is being rotated as a result of the difference of phase between the two sinusoids. And this is exactly what happens in an induction motor. We have two sinusoidal currents applied to the coils at right angles, X and Y plates. One is delayed with respect to the other. In this case, we have this coil, the current is delayed with respect to that one, and I know that because the coil's going that way round. It comes to this one first and then to that one. If I reverse the current in the second coil, then I'll reverse the phase of one of the sinusoids, which will mean that it's now preceding the phase of this one, which before it lagged behind. As you can see, the coil is slowing down because it's now not going with the field, it was going against it, and it speeds up in the opposite direction now with a reversed rotating field. So, you can now see that if you add these two waveforms in one central space where the coil is, you can produce a rotating magnetic field. That's the first point I wanted to make. Now, the second point relates to the analogy that Professor Laithwaite drew between a ping pong ball being carried along in the trough of a traveling wave. The point is this, that it's not a true analogy in that the coil in an induction motor always lags behind the wave a little bit. If it were not the case, there would be no current induced in the coil and there would be no force applied to it. You remember Faraday's law states that the EMF induced in a coil is proportional to the rate of change of field. But it's a change of field of the coil relative to the magnetic field. So that if the two are rotating at exactly the same rate, there'll be no voltage induced in the coil, no current will flow, no magnetic force will act on it, and it won't rotate. But actually it slips behind a little bit, experiences a force, and rotates. In gramophone motors, which go very nearly at the speed required by the AC mains, there's very little friction, so there's very little slip. Induction motors used in machinery, in factories and so on, are designed to carry heavy loads, and so they have to be designed to ensure that even a small slip will generate a large current in the coils and so generate a large force to carry the load that's being put upon the motor. So those are the 2 points I wanted to make, and that finishes my description of the induction motor, and I hope you've been able to see that induction motor is a very good illustration of the 3 principles of electromagnetic induction that have been dealt with in this course, and shows how they can be combined together to produce useful machines.